Right, I want to go through with you now the rules for finding the gradient function. I think you've done your time and you've earned the right to know what the shortcut is now. So given, like I said in class today, given any function has a gradient function, and the purpose of it is to deliver the gradient or the rate of change at any point on that curve or in that function. So just firstly, perhaps we just go through some notation. If we're talking about this, if we've got function notation like so, then f dash x will be the gradient function. So perhaps I need to just draw up a little table here. Function, gradient function. And remember, whenever I say gradient function, I'm talking about the derivative. And if you're asked to derive, you're asked to find the gradient function or the derivative. Right, so just for some notation, this is what we're doing here. Perhaps I needed to make a note of that. So if our function is written like so, f of x, then we would write our gradient function as f dash x, like that. If we have, in terms of y, so y equals, this is f of x equals, then we'd say f dash x equals. If it's y equals, then we write either dy dx equals, you'll see that, or y dash equals. That's how we would, I think it's really important at the outset that we get our notation right. So I think that's it for now. That's pretty much all we use. So function notation f dash, and if it's y dash or dy dx. This means the derivative of y with respect to x. So it says the same stuff. Okay, so what's the rule for it? Well, we talked today about what happens, and let's put that more formally into a rule now, if you like. So if f of x is equal to some constant by x to the power of n, then, or I could just say then, if f of x equals that, then f dash x will equal, so this n and k get multiplied together, so we'll go kn by x to the n minus 1. So we just drop that power by 1. Or another way of writing this is to say, or the derivative of kx to the n is equal to kn x to the n minus 1. So what this here says is the derivative of, or the gradient function of, that function. That's what that bit there means. The derivative of that function with respect to x. So you might see that sort of thing as well. And if you're asked, if you read your translation of that is, I need to find the derivative of that. There you go. Okay, so it's just a bit of strange, odd notation going on with this, and we need to be clear on that. As always, with anything you do, the language is really important. So let's get into some examples. This is not going to be a protracted lesson by any means. Just want to get some examples so that when we get into class tomorrow, where we can rip out some more work from 19B, and we can start to get used to finding derivative functions and getting really good at them. So let's have a look. So let's have a look at, I'm going to use this sort of notation here, the derivative of, let's say, x to the 5 minus 2x cubed. I'm just pinching this from the textbook, plus 2. So the derivative of that will be equal to, okay, so using this rule here, that 5 comes down, and we reduce the power by 1. This 3 comes down, gets multiplied by the 2, so it's 6, and the 3 gets dropped by 1 to 2, and the 2 disappears. Remember, constants, numbers just go to 0. So there you go, there's the derivative there. Or we might say, fine, I'm just going to get practice at using find f dash x for f of x equals 3x cubed minus 6x squared plus 1. So we'll go to work on that. So therefore f dash x equals 3 comes down, multiplies by 3 to 9. We reduce the 3 by 1. 2 by 6 is 12. Reduce the x power by 1, we're just left there, and that disappears off the end. So there's the derivative function for that. So what we could do is extend this further and say, therefore, find the gradient of f of x at x equals 1. So we'd say, okay, well the gradient function is f dash, so f dash 1, I'll put 1 in here, 9 times 1 minus 12, which is equal to minus 3. So there's the gradient at x equals 1 on this function here, using the gradient function. Excellent. Alright, another example. Okay, just two more examples from page 548. We're going to find dy dx, so again the derivative function for y equals x plus 3 squared. Now the way to go with this one is to expand, so we'd go x squared plus 6x plus 9, remember it's twice the product of those two goes there, and then it's x squared and 9. So y equals that, so dy dx, just following suit using the notation that's been given in the question, x squared becomes 2x, 6x becomes 6, and 9 drops. So there's the result. Okay, just one more. So find f dash x for f of x equals x squared plus 3x over x. Now in this case this looks a bit messy, but in fact what we can do is just divide through by x. So we can rewrite this as that goes, and that becomes 1, so it goes to x plus 3. So f dash x is simply 1. X goes to 1 because there's a 1 out the front there, and 3 disappears. So our gradient function is just 1. Alright, that'll do. Exercise 19b. So we'll go with the work requirements from question 2 onwards in class tomorrow. I'll see you then.